So just a reminder, the 9 and 10 homeworks are up. And we'll be taking the 9 and 10 tests when we get back. Obviously, we still got a half day tomorrow, but I don't know. I might lecture a little bit right now. Huh? Oh, yeah. Y'all need to be here. Actually, here. Let me freeze. And
8:05.
y'all have it?
8:05? This class starts at 8:05. Oh, if that's when the bell rings for second grade. That's when we need to be here.
Yeah,
Late arrival. Late arrival, we should be here by 8:05.
Don't have late arrival.
This class starts at 8.
Schedule.
8:05.
Okay, got it.
So I get to leave at 10:35.
Yeah, if you have 2 early release periods, then yeah. Bye-bye. Have a nice day. It's a short day. Yes, half day is here. So if you have a first period, you need to be here at the normal time, 7:40. Is that right?
No.
Yeah, 7:40 is when the tardy bell rings.
So it's like
Yeah,
7:35 is when the
first bell rings.
the first bell rings. Yeah. And so be here around 7:35 if you have a first period. If you don't, be here before 8:10. 8:10 is the tardy bell for second period. And then it goes through this. Remember, no activity period on early release days. We go straight from second to third, which always makes me sad. I want that activity period on an early release day, even if it's just like 5 or 10 minutes. Give me an activity period. But yes, this is the schedule. Everybody be safe over the holidays and try not to spread the virus around. I don't know if we're coming back or not. Did I say yesterday to watch out for Waxahachie and Ennis?
So you think like if they say
Yeah, I think if Waxahachie and Ennis don't come back, I'd be surprised if we do, and vice versa. See, good job. That's awesome. That's where I'm at. Just watch them and see what they do. That being said, we've had a lot of cases lately with students and teachers being out, and for some inexplicable reason, they think it's a great idea to have a potluck today. So everybody's bringing food from home. They're all going to eat in the same room together and touch each other's food. No, I'm not doing that. I'm eating in my room. I'm eating my turkey chili that I made. And I'm eating in here by myself with the door locked, like I do every day. I might go have. I'm probably gonna go have Thanksgiving dinner at my parents' house, just with my parents and me and my wife. And but we're gonna wear masks and stay socially distanced and try to do all the proper things to not get sick. But yeah, if we try to come back and there's a bunch of teachers out, blame it on the potluck, because I think that's a bad idea. So today we're gonna start on a new chapter, a wonderful new chapter. Moisture, clouds, and precipitation. This is actually something I like. This is the one part of well, not the one part, because I do like the weather part itself with the fronts and the weather maps that we'll do for the signature assignment that we will do when we get back. But this is a pretty nice chapter. I like this chapter. Moisture, clouds, and precipitation. It's kind of a nice marriage between chemistry and geology, because we use quite a few of the different concepts that we kind of covered in chemistry. What's happening? It's like the second time we've dropped that today. Got butterfingers. So let's get straight to it. We're going to start off with heat energy. And heat energy, the unit of heat energy that we use is calories. And it's the same, not the same, but it's related to the calories that we eat. In fact, the only difference is a capital C. So you'll notice if you look on your food packages, calories has a capital C. In chemistry or in geology, it's going to be a lowercase c, or I guess even in biology. The difference is one lowercase c calorie is 1,000 of the uppercase C calories. And so it's almost like the uppercase C is a kilocalorie for the lowercase one. So if you eat just 1 calorie of food, that's going to take your body the amount. Wait, what am I trying? How am I going to say this? That in order to burn off 1 calorie that you eat in food, your body has to produce enough heat to raise the temperature of 1 gram of water 1 degree Celsius. Actually, no, wait. Your body has to produce enough heat to raise the temperature of 1,000 grams of water 1 degree Celsius. And so that's 1 calorie of regular food calories with a capital C. So a regular calorie in chemistry is the heat necessary to raise the temperature of 1 gram of water 1 degree Celsius. That amount of heat is what's considered a calorie, and we're going to talk about that with changing phases. Latent heat. This is, I read this earlier and I was like, I'm not doing a good job explaining this because these bullet points do not do a good job explaining it. What latent heat is the heat that is required to change phases from solid to gas or gas to liquid or liquid, whatever, in between solid, liquid, and gas. At that point, you don't change temperature. Does that make sense? So, like, let me do like a little graph here. I need a marker to do a graph. But as you're trying to boil water, right? You start with room temperature water, and so let's see. We got time down here, and then, well, both of these would have T's. Time and temp. And as I try to boil water, my temperature is going to come up and up and up and up and up. And then once it starts boiling, I'm not actually increasing in temperature beyond a certain point, because without some other thing entered into it, liquid water can't be above a certain temperature. If it goes above a certain temperature, it's going to be gas, right? That temperature from Fahrenheit is what, 212 degrees Fahrenheit or 100 degrees Celsius. So at 100 degrees Celsius or 200 degrees Fahrenheit, your temperature is going to level off. And as long as there's water in the pan and it's still boiling, it's going to stay at that temperature. I'm still putting heat in, but that heat is not going to raise the temperature anymore. That heat is going into converting my liquid water into my gaseous water. And this time frame in between where I'm converting from a liquid into a gas and I kind of have both going on, this is where my latent heat is involved. And that heat doesn't go to raising a temperature or lowering a temperature. So that's why they say not derived from temperature change. It's not adding to the temperature change or taking away from it. It's only going between the phases. It's using it to go from one phase to another. And so I feel like that's a better way to explain it. In fact, let me give you the actual Google definition that I Googled here. Latent heat, also known as latent energy or heat of transformation, is the energy released or absorbed by a body or a thermodynamic system during a constant temperature process, usually a first order phase change transition from like liquid to solid or solid to gas. And so, no, gas to liquid or liquid to gas. Solid to liquid, liquid to gas. My bad. I've been doing a lot of this today. And I have a hard time pronouncing adiabatic. So I might mess that up a couple times. But that's what latent heat is. It's the heat that's involved in converting from one phase to another, not necessarily changing your temperatures. So we're going to get into the phases, solid, liquid, gas. If we're talking about water, we have ice, water, and water vapor. To change state, heat must be added or absorbed, heat must be added or released, absorbed or released, depending on how you want to say it. So they go through the two flip sides of each different process. Evaporation and condensation are a back and forth process between liquid and gas. So evaporation, your liquid is turning into a gas. Condensation, your gas is turning back into a liquid. it requires 600 calories per gram to change that liquid into a gas, or vice versa. If you're evaporating things, you're heating them up, and that's added in. If you're condensing things, you're cooling them down, and that's energy is being released by the warmer gas to turn into a liquid. So that is called the latent heat of vaporization, or the latent heat of condensation. The amount of energy put in to change it from a liquid to a gas, or a gas to a liquid. For evaporation and condensation, it's 600 calories per gram of water. Now, melting and freezing is only 80 calories per gram of water. So to turn a solid to a liquid, melting ice, it only takes 80 calories per gram. That's the latent heat of melting. Freezing is going to be the exact opposite. To freeze something, I only need to take 80 calories out to turn a liquid into a solid. And so that kind of makes sense. It seems, just in my brain at least, it seems a lot easier to freeze or melt something than it does to like boil water into gas. For freezing, you can put an ice cube in the freezer for just a little bit, and it doesn't take long to start to freeze. For melting, you can melt ice cubes really, really easy. You don't even need hot water. You just put it in like lukewarm water, and it melts pretty fast. To boil water, you have to turn the heat on the stove like pretty high, and it's got to sit there for longer than you would think it does just to even start to boil. And imagine like waiting for an entire pot of water to just completely boil away into steam. That would take quite a long time. So freezing and melting requires a lot less temperature change than, or heat added, I guess I would say, than condensation or evaporation. Now, we have the two that we don't really talk about a lot because they don't happen as much in our everyday lives: sublimation and deposition. So if freezing and melting is 80 calories, and condensation and evaporation is 600 calories, to skip that middle step, you need 680 calories. So sublimation is going straight from a solid to a gas. You skip the liquid phase altogether, and you just get heated up so quickly that you go directly from a solid to a gas. Deposition is the opposite, going from a gas to a solid without going through the liquid phase. That's going to require removing 680 calories per gram of water. Their example of deposition, I was trying to think of one earlier: ice forming on like your car windshield or your window at home. It doesn't get too cold here for that to happen very often, but it does happen a couple times a year. And so this ice formed directly from water vapor that was in the air, and it got so cold enough that the water vapor went directly from vapor into a solid. Now, this is not the same as like if we have sleet or freezing rain and that kind of piles up on your windshield. That'll be kind of different. But they also have our little graph here showing whether we have heat put in, which is going to be your red arrows. I'm adding heat to melt from a solid to a liquid. I need to add 80 calories. To evaporate from a liquid to a gas, I need to add 600 calories. And to sublime from a solid directly to a gas, I need 680 calories added. If I go the opposite direction, going from a gas to a liquid, I'd take 600 calories out. Going from a liquid to a solid, I'd take 80 calories out. Or depositing from a gas directly to a solid, I need 680 calories taken out. So that's kind of a little like a energy budget for changing from different phases of water. Now, the amount of water vapor in the air is your saturation level. Fully saturated air is air filled to capacity with water vapor. That capacity is temperature dependent. So hot air can hold much, much more water vapor than cold air can, which is why generally you don't have cold, humid days. You just have hot, humid days. So when it's hot outside, you can really feel that humidity. When it's cold outside, it's generally very dry because that cold air can't hold very much water vapor. Don't know that water vapor also adds to your pressure. You just have more molecules floating around in the air. They're going to combine with the sides of a container more often and create more pressure, which they refer to as vapor pressure. So they have two little examples here with a beaker that has a thermometer and a plug in the top. So nothing's really coming or going out of this closed system. And what they're doing here is they're adding water. You can see the temperature is the same, 25 degrees for all three beakers. As they add water, the relative humidity is going to change, but the saturation mixing ratio is going to stay the same. So what the mixing ratio is the mass of water vapor in a unit of air compared to the remaining mass of dry air. So here we have, they don't give us the whole mass. Oh, no, yeah, they do. 20 grams is the total here at 25 degrees. So 20 grams per kilogram is your mixing ratio. The relative humidity is going to be a percentage of how much water you could fit in if you were at like full capacity versus how much you actually have. So here we have 5 grams of water vapor in here, but 20 grams is what we could hold. So 5 out of 20, 5 can go into 24 times. So that means we have 25% humidity. Not very high. That's like kind of a standard thing. I don't think we would feel super muggy if we were 25% humidity. So as evaporation happens, I'm going to get more water vapor happening in the air. My temperature is still the same, so it can only hold so much. But as evaporation happens, I go up to 10 grams of water vapor in the air. So my humidity, my relative humidity doubles. It's now going to be 50% because I have 10 grams in the air and I can hold up to 20. If I evaporate even more, you can see I have less water sitting in the bottom now. That evaporation causes my dissolved water vapor to go, or my water vapor to go up to 20 grams, which is the max that I can hold. And so I'm at 100% humidity. Anything else that evaporates here is just going to condense in the side, kind of like precipitation inside the beaker, and it's going to fall back down to the bottom. So I've reached my maximum amount of water vapor that this little beaker system can hold. I don't know if they're heating this up to make it evaporate, or if they're just saying it's naturally evaporating. But that's a pretty cool little demonstration there to kind of show you the amount of water vapor that each little system can hold. Now they're going to do something a little bit different. They're going to take that same beaker and they're going to change the temperature. And so they're talking how your relative humidity can change based on the temperature. Changing the air temperature, lowering the temperature raises the relative humidity, and eventually, if you get to the dew point temperature, the dew point temperature is the temperature to which a parcel of air would need to be cooled to reach saturation. Once you reach saturation, water starts to come out. So in the mornings, when you cool down, where's that? Cool down the air, and it gets to the coldest part of the morning. When you come out, what's on your windshield and what's on the grass? Dew. And that's condensation that's actually come out of the air because your air is close to the saturation point, or it's closer to the saturation point. So it's much easier for that moisture to come out. Where in the middle of the day, even if it's nice and muggy, you're not going to get dew because you're not close to that dew point temperature. So what we have here, we have 7 grams of water vapor in this beaker. At 20 degrees, you are only at 50% humidity. So it could hold up to 14 grams, but it's only got 7 in there. We're not anywhere close to having water actually come out. As you lower the temperature down to 10 degrees, it changes our mixing ratio. The mixing ratio comes down to 7 grams, and we already have 7 grams in there. So we're at now 100% humidity. If we lower the temperature anymore, this water going to start to come out of condensation. Like, you can't have more than 100% humidity. So as they continue to lower the temperature, it lowers the mixing ratio down to 3.5 grams, which is more than the water vapor that we have in there. And so you have condensation happening. You're not going to see it actually raining inside the beaker, but what's going to happen is you're going to have condensation form on the inside of the beaker. It's going to run down to the bottom and start to pool up there. And so your relative humidity is still at 100%. It just has less water in there because it's actually started to rain out and collect down there at the bottom. So you can see that without really adding any more moisture, we've lowered the temperature and caused it to rain inside the beaker. Now, for a second, I was like, did they put a picture of beer in here? But I think those are ice cubes, so we can comfortably say that this is either a glass of tea or a like cream soda. Does anybody enjoy a nice cream soda? I like cream soda, and my wife hates it. So there you go. But we still love each other. We get along despite that. So yeah, this is either a tea or a cream soda, and you can see the condensation on the outside. And they're just showing you the humidity, the relative humidity curve is inverse from your temperature curve. So when your temperature gets the coolest, right in the morning, when we're kind of waking up around 6 a.m., 7 a.m., it's the coolest, and the amount of water the air can hold is the lowest point at that lowest temperature. So your relative humidity is going to be the highest. No matter what kind of water you have in your air package, it's going to be closest to that dew point temperature. It's going to have the highest relative humidity. As you heat up throughout the day towards that 5 o'clock hour where we generally peak out in temperature, your humidity is going to go lower and lower and lower, because your air is actually capable of holding more water. So it's not necessarily the amount of water that's in the air, it's what the temperature is and how much it can actually hold. Their example here is you cool down the glass, the air around the glass gets colder, which actually raises your humidity to the point where you start to get water condensing around the outside of the glass. Wonderful. So now, how do we measure humidity? The name for a tool that measures humidity is called a hygrometer. There's probably some interesting story about why it's not a hydrometer, but a hygrometer. So, hygrometer is humidity in the air, and there's two different ones: a psychrometer and a hair hygrometer. A psychrometer compares temperatures of a wet bulb and a dry bulb. So, two different thermometers. One of them's wet, one of them's dry. The larger the difference, the lower the relative humidity. If there is no difference, if they're both thermometers read exactly the same, you have 100% humidity and the air is saturated. So that's kind of how that works. The hair hygrometer reads humidity directly, and they don't give any explanations of those or how they work. But here is your, what was the other one called? A psychrometer. And so in a psychrometer, it's hard to see in the picture. There are two thermometers right here. One of them's a little bit shorter, the other one's a little bit longer, and it has like a cloth around it. You dip the cloth in water, so the end of the longer thermometer is wet, and it's going to stay wet. And then you essentially like twirl it around. You twirl it around, and at some point in time, the wet one will kind of like stabilize and not change temperature anymore. And then you read it, and you see how far apart they are, and that will tell you whether you have high humidity or low humidity. The further apart they are, the lower your humidity. If they're the same temperature, you have very high humidity. So this is also going to be, I believe, is this a humidity map or a temperature map? I'm going to assume it's a humidity map, because a temperature map should not have reds being your coldest temperature and blue being your highest temperature. So let's assume this is humidity because it's also on the page with a hygrometer. So in the south, the deep south really, and the east coast over here, you have high humidity. Just to the, is that really the west of the Rockies? Nah. But anyways, right around here you have your lowest humidity, which is going to be your desert states: Arizona, New Mexico, Utah, southern Colorado. You're going to have low humidity there. And then, yeah, up here in the Northeast, you do have higher humidity, or Northwest in the central part of the country, but that's going to change on a daily basis and on a monthly basis. So again, they could have put like just a little sub note there to tell us what's going on in that map. Now, the word I have really hard times pronouncing, and I've gotten better first period, but I was doing very poorly first period. Adiabatic. Adiabatic temperature changes, and actually, this is another thing I did a poor job explaining first period, so this is why I'm re-recording the video. I have no shame in that. Adiabatic temperature changes, or adiabatic processes, are basically um, when you're not really changing the amount of heat you put into a system. So I'm not making things hotter. I'm not making things colder by adding or taking away heat. But the temperature is changing because of elevation, essentially. So their definition for adiabatic, which let's listen. Adiabatic. Adiabatic. Uh, Relating to or denoting a process or condition in which heat does not enter or leave the system concerned. So we're having changes in humidity, we're having changes in temperature, but there's no heat getting added or leaving out. It's all in changes of position of the air. And they go through that a little bit, but they didn't explain it super well in the PowerPoint. So adiabatic temperature changes is where air is compressed or it expands. So when it's compressed, the motion of your air molecules increases, the air warms up, and your descending air is compressed as it drops down because up in the atmosphere you have less pressure, you're not compressed. As you drop down towards the ground, you're going to have more and more air pressure. Your air is going to warm up, and you're going to get results of a lower humidity because your air can hold more moisture. The opposite is going to happen if your air expands. If it rises, it's going to expand. As it expands and rises, it's going to cool down, and your air is not going to be able to hold as much moisture, so it might start to precipitate. So now we have two different types of adiabatic rates. We have a dry adiabatic rate and a wet adiabatic rate. The dry one is basically your air hasn't reached the saturation point. And they have a rate for that, which is every 100 meters that you rise or fall, you will change 1 degree in temperature. And we kind of see that as you go up through the mountains. You get different temperatures as you go higher and higher in elevation. It's going to happen the same way on the way down. If it's descending, every 100 meters it descends, it has a 1 degree temperature change. The wet adiabatic rate is a little bit different because you have reached your condensation level. You're at 100% humidity, and any temperature changes you get are either going to change your vapor to liquid or liquid back to vapor. So air has reached the dew point, condensation is occurring, and latent heat is being liberated through those processes. So heat released by the condensing water reduces the cooling rate, and basically you have less than that 1 degree Celsius. You have a half a degree Celsius to 0.9 degrees Celsius for every 100 meters. And they show this kind of here. Your dry adiabatic rate is applied all the way up until you start to condense water into a liquid, from a gas to a liquid. Above that, you have a different wet adiabatic rate. So let's say you have this air package here at the surface, it's 32 degrees Celsius. As it rises, that temperature is going to drop. As the temperature drops, my relative humidity is climbing because my air can't hold as much water. I'm not adding any more water or any more heat. It's just rising and changing pressure, which is going to change the temperature. So the same package of air, which isn't really mixing with anything else at this point, is just getting less and less able to hold the water that it already has. And when it reaches condensation level, it's now 100% saturated. It can't hold anymore, and clouds literally start to form at this rate, which is why in general, unless you have a weird atmospheric day and you have low fog, you're not going to see clouds down on the surface. There's a physical limit where below that, if your air is dropping, this liquid moisture is going to evaporate and just go back into water vapor instead of these condensed clouds here. So it kind of works both ways, but there's different levels based on whether you've reached that condensation point or not, which is why they have a wet adiabatic rate or a dry adiabatic rate. Now, orographic lifting has a relationship to the adiabatic rates because mountains can force your air up. And we've seen this before. I think we saw this image when we talked about deserts. But this basically is a snapshot of like the Pacific Northwest because they have these mountain ranges. They have very moist air coming off the Pacific Ocean. And as it comes inland, that air can't go any further inland without going over the mountains. So it's forced to go up in elevation. The temperature drops, the pressure drops, and essentially the air can't hold all that moisture that it got from the Pacific, and it starts to rain. So on one side of the mountains, you will have a rainforest. When it gets over the mountain, it drops back down, it warms up, it gets compressed, and the relative humidity drops. And so what little water it has left in it is just not going to get the chance to rain out at all. It's going to stay dry. And so it's almost like night and day on either side of these mountain ranges. You have like tropical rainforest essentially, or I guess they call them temperate rainforest because it's not tropical, but literal rainforest over here, and then desert on the other side. And I actually pulled up Google Earth to just illustrate this. So, well, it can't get any darker here. Here is your Pacific Northwest. You can see Seattle, Portland. Everything is green, and you can see almost like see the ridge of the mountains here because it goes from green like to this light brown where you just have the rain shadow desert. It's still the same air package that comes over that, but it just gets really, really dry. You got like Yakima Valley where the apples are in Wenatchee. You can just see like how dry this area is. There's a couple little smatterings of some green farmland where we kind of water stuff, but that's really dry compared to the very, very dark greens you have over here. And the patches of white you have right there are mountains. Those are probably Snow Peak Mountains, Mount St. Helens, Mount Rainier, Mount Adams. So yeah, that's a real life kind of illustration of what we're looking at there. The screen just looks so terrible. It looks so much better on my computer screen. I need a new screen. I'm gonna put in a work request for a new screen, and they're gonna deny me. But I'm gonna ask, and I'm gonna make them say no. So yeah, that's your rain shadow desert. Now frontal wedging. This is where we get a lot of our weather here in Texas. Is from cold fronts coming in. Most of the time, relative to the cold front, we have warm air sitting here. It's usually moist because we're close. We're not always super. The air doesn't always come from the Gulf, but we usually have moisture in our air. It's nice and warm. We have a relatively high humidity level, and then this cold air package comes in. Warm versus cold. The cold's going to stay low. The warm's going to be forced upward. And so as this cold air, and if you watch the news at all, they call this like a frontal wedge because it forms like a wedge shape and it pushes the warm air up. As it gets pushed up, the pressure drops, the temperature drops, and the humidity rises, and literally the rain falls out because it can't stay in that air package anymore as it goes up and starts to cool and the pressure is released. So that's why we get these storms. That's also why, in general, we don't have storms that go for like days and days and days and days. We get like one sweeping line of storms that comes through. And after a couple hours, you get on the backside and there's not even storms anymore. And so that's quite a bit different from other areas of the country that get kind of these steady rains or little flash rains that aren't associated with fronts. We almost always get the line of storms. It almost always has thunder and lightning and some high winds associated with it. Not necessarily too damaging all the time, but not like a nice, calm, like even rain that you can sit out on your front porch and enjoy. And so, yeah, that's the kind of weather that we get here in Texas. And we'll spend more time talking about weather, but they just wanted to kind of illustrate this cold air pushing your warm air up, and that adiabatic kind of change happens because your air is rising. Adiabatic. Has anybody been to Florida? I haven't spent much time in Florida, but my experience in Florida was if it starts to rain, just wait a couple minutes because it's probably going to stop very quickly. And that was like new to me because we went on the school field trip, and we're getting our stuff set up, and we're about to go scuba diving. And in Texas, you can't be in the water when it's raining because you're gonna get struck by lightning. Like, you got to get out, you got to stop playing football, you got to do all the things. Like, you go inside when it's raining because we almost always have thunder and lightning. So we're like getting ready to go scuba diving. Not scuba diving. We were not that. We didn't have that kind of equipment. We were getting ready to go snorkeling, like off the side of the highway. Not even like nice reefs, but like snorkeling in the mud. But we're all getting ready and we're getting our stuff on, and you see this thunder, or not thunder, but this like rain cloud coming in. And the professor's like, don't worry about it. Just get in the water. It'll be gone in a couple minutes. And literally it was gone in a couple minutes. It's the weirdest thing I've ever seen. But Florida has that, and that's because of convergence. Your airflow brings these different air packages together, and essentially when they get on top of the continent, they form these little sporadic little rain clouds. And I don't know how common this is, but if you look at this picture, it's kind of amazing. This outline of Florida is not you seeing the actual land itself. These are clouds. And so these clouds here almost like perfectly match the shape of the peninsula of Florida. There's not a lot of clouds going on over the ocean. And so you can see this convergence of these two air masses right over Florida is actually what causes it to rain quite a bit on the peninsula there. And so I like that picture. That's a pretty interesting picture there. And then local convective lifting. This is where we left off. Is the bell about to ring? Wonderful, wonderful. So this is just basically this kind of cycle that happens. The sun shines, which heats up air. If that air is moist, it's going to, not even if it's moist, but a lot of times it has moisture. The sun heats it up, hot things rise. As it rises, it's going to lose pressure and cool down, even though the sun's still shining on it. And so once it gets to that condensation level, it'll form a cloud. The cloud will start to rain. And that's why you have this localized convective lifting, when you can get these kind of rain clouds without really a front or any kind of like storm or weather package. They're just kind of like isolated little showers. So nice. And then maybe not tomorrow, maybe next week after we take the test, we'll pick up here with types of stability and stable air and unstable air, and how we get storms and weather and all that good jazz, and the different types of clouds. Look at all those clouds. Anybody want to be a weather person? Weather's nice. Get to be on the TV. In Texas, yeah. Well, you're the most important person a couple nights a year, but mostly, yeah, you don't do anything. I was mad at the weather guy this morning because old Evan on Fox 4, he went right up to Thanksgiving and didn't tell us what the weather is going to be like on Thanksgiving. So come on, Evan, it's 8 days away. You could give us a Thanksgiving prediction. We're ready for it. I need to know. We're going to be outside. Can I be smoking my turkey the day before? I need to know, Evan. Y'all have a nice day. Tomorrow, oh yeah, we already talked about the schedule. Make sure you're here on time.